Welcome to this webinar on updates to the ERIC flash flood criteria. This is part of the European Flood Awareness System, EFAS, and my name is Richard Alpschull-Wild. I work at the Swedish Meteorological and Hydrological Institute. We are one of 3 EFAS dissemination partners. So this webinar is an update to the flash flood indicator. So the flash flood indicator in EFAS is called ERIC, which stands for the European Runoff Index based on climatology. A longer technical background is available in a previous webinar, which is on efas.eu. This webinar is focusing only on updates that have occurred over the last 18 months. So a brief background, however, is that the ERIC indicator is a comparison of forecasted surface runoff, which is accumulated over the upstream area, with a reference threshold. So it's a combination of COSMOLEP's precipitation forecasts from the 20-member meteorological model and soil moisture forecasts from the Listflood hydrological model. And these two things are combined into the ERIC indicator. This is done for 5-day forecasts for catchments smaller than 2,000 square kilometers. So it's worth remembering that EFAS formal notifications are issued for catchments larger than 2,000 square kilometers, and EFAS flash flood notifications are issued for catchments smaller than 2,000 square kilometers. Also important is that the definition of flash flooding in EFAS is still related to rivers or watercourses. We're not referring to flooding in urban areas from pluvial events. So the diagram below shows briefly how the ERIC indicator is derived. First we have the COSMOLEP's ensemble precipitation forecasts, which are run twice per day with 6 hourly time steps and a 5-day lead time. And these forecasts, of which there are 20 members, are run at 7 by 7 kilometer horizontal resolution. The Listflood model then provides us with the ensembles of soil moisture forecasts at a 5 by 5 kilometer resolution, and these are combined together into the surface runoff forecast at 1 by 1 kilometer, so they're downscaled to the river network. They are then accumulated for all grid cells with an upstream area less than 2,000 square kilometers, and they're accumulated over 3 different time periods: 6 hours, 12 hours and 24 hours. The maximum of these 3 accumulated time periods is then taken, and it is compared to a 19-year climatology. So there is a climatology that is derived for 19 years based on the COSMOLEP's reforecast dataset. The comparison is the forecast value with the climatological value then gives a return period, and that is what is displayed on the EFAS interface as the flash flood ERIC indicator. If we have a look at what you can see if you log in to the EFAS interface, and these layers are available under the flash flood layers, there are 2 ERIC products. So we're focusing here on the ERIC products. The first is the reporting points, which is called ERIC reporting points, and these are points in the river network which are highlighted because their flash flood forecast probability meet 2 criteria. The first criteria is that the probability of exceeding a 5-year return period is greater than or equal to 10%. And that's important to remember because 10% probability, in this case there are 20 meteorological forecasts or ensembles, so that means that approximately 2 members are exceeding the 5-year return period. And we also say that the forecasted start date is less than 60 hours. If these 2 criteria are met, then we receive in the interface a triangle which shows us where flash flooding may occur in the forecast interval. Also worth pointing out now is that this number, 60 hours, is not the same for which we issue notifications. Notifications are issued for a maximum of 48 hours. I will, on the next slide, explain why this is the case. The other product that you can see is the ERIC affected area, and this is the river network which contributes to each ERIC reporting point. So these are the areas that are at risk from flooding. So for example, with this point here, which has a 14, the upstream area, these purple grid cells. So this is the catchment area contributing to this ERIC reporting point. If you then click on one of the reporting points, you can see a graph, and that graph shows you the ERIC indicator expressed in terms of return period for the forecast period, and you can see all the different ensembles and the percentage exceedance probabilities for each return period: 2-year, 5-year and 20-year. So a number of changes were implemented during 2019 and 2020, ongoing now. Starting with what was done previously, it was observed that there were fewer ERIC reporting points after the release of the extended domain in 2018. Additionally, the LISVAP routine was released in 2019. LISVAP was the introduction of the Penman-Monteith evapotranspiration routines into the LISFLOOD hydrological model, which had an impact on soil moisture, for example, which is used in the flash flood indicator. So therefore a new validation was performed against heavy precipitation observations from the European Severe Weather Database. And this was done for the period 1st of June to 31st of August 2018. The EFAS flash flood notifications were then optimized to have the best balance between hits, false alarms and misses. And this combination is known as the Critical Success Index, or CSI. There are a number of graphs on the left hand side of the screen. If we focus on the top two graphs first, these are showing the Critical Success Index, CSI, for the 2-year return period and the 5-year return period, both for this period June to August 2018. And then each of the lines is a different lead time, LT. So we have 0 to 24 hours, 24 to 48 hours, 48 to 72, etc. The important thing from these two graphs is simply to observe that the Critical Success Index is highest for the blue line in both cases, for the 2-year and the 5-year. So the blue line is the 24-hour to 48-hour lead time, and that is the reason that has been, the 48 hours has been chosen as the criteria. The CSI values are very low for all exceedance probabilities. So along the bottom of the graphs we have exceedance probability from 0 to 1. So for example, an exceedance probability of 0.2 means a 20% exceedance of that return period. The CSI values are very low because there were a large number of misses when this analysis was done. And that is because the database, the Severe Weather Database, includes very many small-scale pluvial events which are subscale to the ERIC forecasts, and therefore it looks like there are lots of misses, but these are not events that we would expect the ERIC indicator to capture. So, in any case, the criteria of 48 hours is chosen because it gives the highest CSI. Then the bottom two graphs show the number of hits and number of false alarms, and also the hit rate. For the 2-year exceedance probability on the left again, and the 5-year exceedance probability on the right. And here, for example, if we look at the 0.1 or 10% exceedance probability, you can see that for the 2-year return period, that would give us approximately 40 hits and just under 80 false alarms. If we do the same thing for the 5-year, we would get approximately 20 hits and just under 40 false alarms. So the 2-year return period actually gives a higher hit rate, but at the expense of issuing more false alarms or false warnings, notifications. So for this reason, the 5-year return period was chosen in order to reduce the number of false alarms, even though that reduces the number of hits as well. So the optimum solution that was derived from this analysis was that the 10% exceedance probability would be used for the 5-year return period with a lead time of less than 48 hours. This map shows the locations of those heavy rain events with mentioned in the analysis flood impacts for this period 1st of June to 31st of August 2018. And what's important to show from this map is that there are a number of locations that did not have data. So for example, much of the United Kingdom, Ireland, even parts of France, Spain, Portugal and other areas in mainland Europe missed or did not have very many data points. So therefore the analysis is being redone for a number of reasons. The first reason is because we are soon going to release the EFAS 6-hourly calibration, and therefore it's necessary to re-evaluate the thresholds using the soil moisture time series from the 6-hourly calibration, but also using additional flash flood events will improve the analysis, and this is being done at the moment for the UK and for Austria, and these results will be available soon. So it's very important that if you have information on historical flash flooding events, that you share this data with the EFAS development team, because this can then be used to improve the flash flood criteria. Lastly, a number of changes have also been implemented during the previous 18 months, which are about improvements to visualization. So these aren't technical changes, but they're changes in the EFAS interface that have improved visualization. The first of these was a redefinition of the administrative regions that are used to issue flash flood notifications. So these are now based on NUTS level 2 and NUTS level 3 from Eurostat 2016 and GADM. And basically what this means is that the administrative regions have been redefined so that they are equally sized for the whole of Europe, because obviously it's important, if flash flood notifications are being issued based on administrative units, that the administrative units are equally sized. And these can be seen on the static layers on the EFAS interface. Secondly, the visualization has been improved by showing one enlarged triangle per administrative region. So previously all the triangles had the same size, but now the triangle that is most flash flood prone, so that is the one with the largest exceedance probability, is shown as an enlarged triangle in that administrative region, which makes it much clearer when trying to identify which point is most flash flood prone. And finally, persistence has been introduced. When you click on a flash flood reporting point, you will receive a dialog that looks like this, and there is a new criteria here called persistence. So that is the number of prior forecasts with a probability greater than or equal to 10% of exceeding the 5-year return period. So in this example there are 6 forecasts, which means the current forecast plus 5 before it met this criteria. And this is very useful because it means that you can be more sure that this event is likely to occur because it has been present in the previous forecasts. If the persistence was only 1, that would mean that this event was only present in the current forecast.